terms of getting this done, and away we go. All right, so ask questions. The one thing I need to say today is I need to be gone by 4 this afternoon, so if you're trying to find me, do it before 4, right? Find me before 4 o'clock. Now, ethers. Ethers are very useful. Ethers are obviously closely related to alcohols and to aldehydes and ketones. You'll find that ethers don't have a great deal of chemistry of their own, which is kind of useful because we can use them as solvents or things like anesthetics. They don't react with very much. They will do some chemistry, and most of it will be stuff you've seen before. Most of it will be SN1, SN2 chemistry, so this might be useful for some review from last term. To give you some structures, some ideas of where these things show up. Many of you are interested in biology, medicine, pharmacy, things like that. There's the generic structure for an ether down at the bottom. You can see here some carbon group attached through an oxygen to another carbon group. They are related to alcohols. We'll make them from alcohols today, but they don't have a pKa. They don't have an appreciable pKa because there's no proton there that you can think of as being acidic. We're going to use them maybe to block alcohols, maybe to cap alcohols after we've made an alcohol. Now, in terms of where these things show up, you can see here melatonin, an interesting hormone. Many of you will have to deal with these types of pictures in the future. They're not that complicated. We will build up towards those. Morphine is still a very powerful analgesic used to alleviate pain. And you can see here lots of functionality. This is a great molecule. You can see here alcohol, pKa of what approximately? 16. Phenol over here, pKa of what approximately? 10. So we can start now to have some good opinions about what's going to happen here. By the end of the semester, we'll be through amine chemistry. We'll talk about their nucleophilic characteristics and their basic characteristics again. But this molecule now is realistic. It's starting to look useful and starting to look quite impressive. But you can see over here the ether function. There's the carbon, there's the oxygen, there's the ether, holding those two rings together to make that system rigid. On the right, we've got vitamin E, which apparently is an antioxidant. And by now, from the last chapter, you should recognize there's the phenol type structure, which might have some antioxidant properties, and obviously that's an important biological molecule. So plenty of examples of these things. We're not going to spend all day looking at systems. We're going to look at what they do for the most part. For pharmacy, people have to look at these structures, and I don't know if you memorize things in pharmacy like this, but these are some interesting ether-based molecules. And again, the ether is very useful because it doesn't break apart under normal conditions. Under physiological conditions, usually you don't metabolize ethers. We'll see why in a minute. But over here, we've got this Prozac with an ether linkage right there and a chiral center next to it. Tamoxifen is an anti-cancer drug. There's your ether right there. Again, be able to look at a molecule and identify the functional groups. Be able to pick out the important bits and pieces as we study them. And over here, one of the blood pressure treatments, there's a carbon, oxygen, carbon. Again, it's a very useful linker. It's a very useful way of attaching two pieces together through what I'll describe as a robust linker. In other words, it's going to last and it's not going to be easy to break down. So there are many of these things out there, and we have to be familiar with them. Now, in terms of nomenclature, again, much of this is up to you. It's fairly dry stuff, and it's just following on from stuff we've seen before. And again, just to be, actually to be useful, there are two ways of doing this. Okay, there are two ways of naming ethers. The first one would be the simpler one, where you just call it an ether as the parent molecule, and then you go for the substituents. And it's not the larger group before the smaller group. It's all about alphabetization, so therefore ethyl methyl ether should make sense. And on the right over here, tert-butyl methyl ether. Don't forget that the T does not count if it's hyphenated. It does count if it's part of the word. So isopropyl, I counts. T-butyl, T does not count. Don't forget those things from last year. Now, we can also, if things get a bit more complicated, do the substitutive type of nomenclature like we did last year, where you call this thing something pentane, and you decide there's two carbons, so that's ethoxy. That's fairly easy, right? Oxygen, ethoxy, and it's substituted on a pentane, so let's call it ethoxypentane. And again, practice, you're not going to see a lot of nomenclature in terms of being tested on it, but you need to be familiar with it to be able to converse in the subject. Properties of ethers, again, this is picking up the pace. Feel free to stop me. Again, you are the handbrake. I will just fly if you don't stop me, so ask questions as we go, but I think this stuff is fairly tame. Now, last year we developed ideas of hybridization patterns. sp3 typically was tetrahedral in shape. If you had a perfect tetrahedron, like in CH4, the bond angles were 109. But in this case now we have water, and even though it's tetrahedral, because you have two lone pairs here which take up the other two valences, it isn't 109. What was the argument there? Why is this smaller than 109? Lone pairs will take up more volume, they repel more, and so therefore you get some compression of the bond angle down to 105. Now if we start adding groups, we can see it goes back up to 109. So something's happening here that takes you back to more of a sort of a regular tetrahedral system. So what do we think it is? We haven't really changed the lone pair characteristics, so it can't really be them. What is the difference between methyl and H? It's bigger, it's large, right? This is bigger, and so we're starting to get a battle now between the lone pairs repelling and the large groups getting in each other's way. Jessica, you okay? All right. Now, on the right-hand side with dimethyl ether, the bond angle got even bigger. And again, you can see now that this is quite large, this is quite large, they'll get in each other's way, and they'll want to repel. What do you think if you went to T-butyl? Even bigger, right? Even bigger. So you start to get away from the typical angles because now we're getting some repulsion, some steric problems. So that's fairly straightforward. For your sort of knowledge in the lab, you're going to do a fairly straightforward lab, I think, coming up with the infrared spectroscopy. We'll talk about that at the end of this week. But you'll find out that some ethers have solubility in water, and that can be a bit of an issue. So if you look down here, why should an ether possibly be soluble in a protic solvent? And the answer is because it has lone pairs, and it can coordinate with an H and do hydrogen bonding. And just FYI for the future, if you look at diethyl ether, which is a nice polar aprotic solvent, it has alkyl groups, which are non-polar, and it has an OC bond motif, which will be a little bit polar. And this stuff has a 5% solubility in H2O. All right, 5% of this will dissolve in H2O. Why is that interesting? Well, you're going to use ether in the future, and if it's wet ether, it'll ruin the experiment. If it's been, if it's been left open and it's absorbed moisture to 5%, your experiment won't work when you do the Grignard reaction. So you need to make sure it's dry ether, make sure that the prep has been done properly, and that you're using the right stuff. Okay? Or else you'll have problems because you have water in your ether, because it absorbs, and you'll kill your Grignard reagent. So just keep on your toes when you're doing labs, and make sure you're okay with that. In terms of properties, physical, this should be sort of second nature by now. These are the typical types of things that they throw at you on an MCAT, PCAT, GRE, stuff like that. Compare the boiling points. Ethanol, we dealt with alcohols a little while back. It has quite a high boiling point for being such a small molecule. If you went to dimethyl ether, you're now down to being a gas at room temperature. And if you go down to propane, which are all very similar in terms of their molecular weights, you're now down to -42. So why is this so low? Why is that a gas? It's non-polar, there aren't dipoles in there, so you have very weak intermolecular interactions, right? Very weak intermolecular reactions. Because don't forget, what boiling is not breaking that molecule apart. What boiling is breaking these molecules away from each other. Okay, intermolecular properties. So over here, the boiling point jumps by 20 degrees roughly, so that means that you probably have something in here like a dipole, and so now we do have some intermolecular interactions, which then take more energy to break, and so the boiling point should be higher. And all of a sudden, you jump 100 degrees there. So what's the property there? Hydrogen bonding, right? That can hydrogen bond to other molecules of itself, and that takes quite a lot of energy to break apart, and so you have quite a high boiling point for it being such a small molecule. So we've seen those things before, nothing too tricky. Down at the bottom, you have the idea of the dipole. The oxygen is more electronegative than the C, pulling electrons away from carbon, giving you overall a dipole. If you worked out, it's in that direction, and therefore it's a little bit polar. A little bit polar means more stuff sticking the molecules together, means higher boiling point. Everybody okay? Dominic. There's no dipole, there's no hydrogen bonding, anything possible, just the usual sort of intermolecular London forces, whatever we call them. There's no delta plus, delta minus in that system, so one molecule of it is not attracted to the other molecule so much. And as you start to go to the ether in the middle, you get delta plus from one molecule attracting delta negative from the other molecule, which holds them together a bit tighter. Takes a bit more energy to break apart. Okay? Now, in terms of ethers themselves, these are very useful to us. I'll show you in a second they're useful in medicine, but in the lab they're invaluable. And we have a series of these types of systems and these types of molecules that we use a lot as solvents. And this will make some sense. If you want a solvent, typically you want that solvent not to take part in a reaction. You want the solvent to sort of sit there, dissolve things up, and not get involved. And ethers are very good at that. They're not very nucleophilic, they're not acidic, they're not basic. They dissolve things up because they're polar aprotic, but they don't get involved. Now, if you look at the simple, again, building off of the boiling points, low, higher, higher still. You are getting more significant interactions as the molecules get bigger. But this is useful to us as chemists because we have molecules down here. This boils at 35 degrees C. And if you want to run a reaction at room temperature, that's great. That will work for you in the Grignard experiment. It's easy to get rid of because it boils so low. That's a really useful solvent. But what happens if you have to boil this stuff? What happens if your reaction is going very slow and the first thing you would do if it's going very slow is maybe reflux it, maybe heat it up, you've got a very limited sort of playing field there. 35 degrees isn't very high. So we can go to something like tetrahydrofuran, which boils about 75 degrees C. It's got the same properties, or very similar properties as ether, but it has a higher boiling point, so you can raise the temperature a bit more. You can speed things up by doing that. And if that doesn't work, often what we do is go to something like 1,4-dioxane, and it boils over 100 degrees. So now you have this much broader range of temperatures to play with to make sure that reaction works. Okay, so you can see that they're all simple compounds with carbon, oxygen, carbon, and you should now be able to identify those structures within a bigger molecule. Okay, nobody's saying anything. I'm going on. Here are examples of anesthetics. Okay, people putting you asleep before a surgery. You can see here the ether compound. Okay, polyfluorinated. I don't know who sells these things or what, but isoflurane, enflurane, sevoflurane, desflurane. They're all very similar compounds. Okay, what do you think about their properties in terms of ozone? Do you think there'd be a problem with ozone or not? Some of these things are going to be problematic, right? Because they're halogen carbon bonds which can break when you treat them with radicals and ozone and stuff like that. But they're still used to put people asleep, and that's because they don't do much in terms of reactivity. Okay, they're not going to react with you, which is a good thing. That's just FYI. What will be important in the near future, I don't know exactly when you do this experiment, but when you do, be ready for it, is the use of ether in the Grignard experiment. Because we know that we can dissolve up RX, simple alkyl halides. They typically dissolve in simple organic materials, but magnesium doesn't. Magnesium's a metal. And when you run this experiment, it's kind of fun because it starts out looking as if nothing's happening. The magnesium kind of floats on the ether. But then you put some iodine in to catalyze it, and you start to warm it up, and all of a sudden, boom, 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 boom. It's like Jaws. It starts to dissolve. It starts to work, and this stuff starts to disappear. Now that's only possible if you use a solvent like ether, where it can coordinate to the metal. Okay, so that's again a good property of ether, which allows us to use this. And you will see on the exams and on the homeworks, this little guy, that's the solvent. And typically, if you can do a reaction in ether with a Grignard, that's the way to do it. Very cheap, very simple, easy to work up. Other properties of ethers, these guys. Why do you think they're called crowns? They look like crowns, right? They look like jewels. All right. These were actually, I think, invented in Dayton. So this is some local stuff. We've got compounds which are cyclic, which contain various numbers of oxygen. And the whole point of these compounds is to project the lone pairs into the middle of that cycle. You can see each of these oxygens has lone pairs, and so we have a cavity in the middle of this thing which is quite electron rich. And you'll see on the next slide that we can actually put metals in there, put positive things in there, and sequester them. So the nomenclature is fairly easy. The 12 comes because you've got 12 atoms in the cycle, and the 4 is because you've got 4 oxygens. Okay, so that's fairly simple. 15 crown 5, the difference now is the cavity in the middle is bigger. Maybe you can put sodium in one, potassium in another, where they've got different size metals. And you can see now 15 number of atoms in the cycle, 5 is the number of oxygens, and finally over here, 18 crown 6. Now these are very useful additives for organic chemistry. They help us dissolve up metal salts that wouldn't dissolve otherwise, but they're highly poisonous. Right? You'll be very careful with these things because they are very, very poisonous. So what I've got here is a picture of how this works. And this is, I think, 18 crown 6 on the left. And you can see from the molecular model that it has this hole in the middle. It has this cavity. The oxygens are pointing towards that cavity with their lone pairs. So what will happen is that you can stick a metal in the middle. The metal is positive. It wants some electron density. It's Lewis acidic. The oxygens are Lewis basic. They can coordinate with the metal, and then it can end up sitting in the actual cavity. Okay? And this is useful for separations. You can separate metal ions doing this, and very useful for solubilizing material. So if you think about some metal and its anion, let's say this thing is a nucleophile, sodium azide, sodium cyanide, and it's not dissolving up in your material, this will help it do so. Because all of a sudden, your sodium or your potassium metal is in the middle of all this organic stuff, and that organic stuff will dissolve up in your solvent. And you'll drag the nucleophile into solution and make it more reactive. So these are used to help in terms of reactivity when our nucleophile is being sluggish, and you want to make it react faster. Got a lot of use in medicine, these things. I'll show you a couple of examples in a second. There's a few anti-HIV compounds out there, I think, which are based on this same idea. And when you get to biochemistry, porphyrins, when you start talking about cobalamin and things like that, you start talking about hemoglobin, things like that. You have this platform in which a metal can sit inside. So here's the example where you want to solubilize your material. KF is not very soluble in very much. It certainly isn't soluble in benzene on its own. It's a very, very polar salt. So what you do is you put the metal in the middle, you dissolve these two things together, and the metal ends up in the middle. Just the right size to sit in the middle of that thing. And because you've now got the metal ion sequestered inside that cycle, that will dissolve. That will dissolve in benzene. And, you know, since this is intimately associated with that, it has to go with it. Okay, so the F minus has to go into solution. All of a sudden, you've got a better nucleophile. You can see here the use, small cycle, you can get lithium in there. Bigger cycle, sodium will go. Bigger cycle, still potassium will go. And maybe we can use that for separation. Jessica. Well, if you have a selection of ions in the solution, the one that fits best will go in there and stay in there. But in terms of solvents, you can use these with whatever solvents you want. And it's just a nice way of enhancing the nucleophilicity by dragging the nucleophile into solution, so it has to be a nucleophile. It's not just floating on top, which is no use to us. All right. I'm not sure if this was actually designed this way or it just happens to be coincidental, but nature does this a lot. Nature produces all kinds of different organic molecules that have this same type of property. Non-actin, I think, is an antibiotic. And you can see here, if you look at that, there's an awful lot going on, but you've got oxygen pointing towards the middle of a cycle, here, 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 and here. Some of them are ethers, some of them are carbonyls. But they all have that property of allowing something to fit in the middle. Okay? So you can sequester some species, maybe a metal ion in the middle of that. Very important one, monensin, which is one of the very few compounds that has any efficacy against pancreatic cancer. This one now, again, it's not a cycle per se, but it can wrap around. Okay, you can see here, basic, 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 all the way around, and that thing can wrap around an ion, for example, a three-dimensional species, and just sequester it, take it out of the game. All right, and you'll probably see a lot more about that if you go to medicine or pharmacy. That's pretty much it in terms of FYI. What everybody wants to do is mechanism. It's Monday for mechanism. This is all review. This is pretty straightforward. If you want to make an ether, it's very simple. Typically, you take an alcohol and heat it up. You need some acid, and you get the ether that comes out. And it's a very simple reaction to run. You can imagine now the alcohol maybe is a higher boiling point. This material is a lower boiling point. You can distill it away. You can distill it away as you make it, and that will allow for the equilibrium to go to the right side. In terms of a mechanism, there's not much to this. The H plus will protonate the OH. What does that do? What's that good? Why is that good? Makes it a better leaving group. Now, if you protonate that particular OH, will it break off on its own? No, because it's primary, and that will give you a horrible carbocation. So if you're going to get a coupling here to give that product, it's not going to be SN1, and the other only alternative is what? SN2. So here we go. Review. This is on the website again from last term. Go and have another look. Protonate in the first step. Pick up the alcohol, simple acid-base reaction. Probably reversible. Get down to here. We're going to have to start worrying about more reversibility in the near future. We know this is the product. How do we know? That comes next week and the week after when we do spectroscopy. We have tools that will allow us to tell that we have the right stuff. That is the molecule that we're making. Now we have to decide how we get there. So in this case, we've got a nucleophile. Is that a strong nucleophile or a weak nucleophile? Weak. A neutral alcohol is a weak nucleophile. So you're going to have to heat this thing up and make it go. And you'll get the SN2 reaction because you can't do an SN1 because it's primary. And that will give you this, and that has to lose a proton. Where does it go? Probably to the solvent or to the solution. In this case, maybe another molecule of the alcohol picks it up, and away we go. And that's probably reversible. Now, in lab, what you've done is you've mixed some acid with an alcohol and heated it up. How much acid do you need? Look at the mechanism. How much acid do you need? Small amount, right? You need a catalytic amount. Number one, it speeds things up because it makes a better leaving group. Catalysis usually has to involve speeding up, right? Lowering the reaction barrier. In terms of what else you need to do to be a catalyst, what else needs to happen? It has to be regenerated. And the last step is regenerated, right? So you don't need much, which is good because, concentrated acids are kind of dangerous and you don't want to use too much. So in that reaction, at the end of this, you've decided that all of this has been consumed and this is what you've got. Now, how would you get rid of this? What type of process do you need to do to get rid of an acid? Okay, you've put some acid in there, the reaction mixture is acidic, the pH is less than 7, but at the end of the day, you want that acid gone. What do you need to do to this reaction? Add some base, right? Add some base. And this is typically the separatory funnel. At the end of the day, when you've done the experiment, you put it in the separatory funnel, and you put some base in. And what does the base do to the acid? Neutralizes it. That's all it is. It's neutralization, right? So you'll see that. We often write it like this, and we can explain that mechanistically like that. But in the workup stage, and you don't have to worry a lot about that this semester, the workup stage, after the reaction's finished and you have to isolate your product, it's often adding an acid or adding a base to neutralize the medium. Nothing more fancy than that. Okay? And at the end of the day, you have a very nice synthesis of an alcohol. Now there is of an ether. There is a limitation to this experiment. Do you think I can start out with 2 different ethers? 2 different alcohols? Do you think I can start out with 2 of those different and expect to get a clean, efficient reaction? No. Okay, no, because you'll get this protonated and it'll react with itself and it'll react with that, and this will protonate and react with its. You'll get mixtures, and mixtures are always bad in terms of isolating stuff. So the limitation or the drawback of that particular experiment is that you have to make symmetrical products. Now down at the bottom you've got some limitations here. It is limited typically to primary alcohols because in secondary and tertiary you can get E1, right? They will support a carbocation and they can give you E1 as well. So this is a good way of making primary systems, not so good for anything else. Okay, other examples? All you need to do here is to make the compound a different shape, and all of a sudden it looks like a different problem. It isn't. It's the same idea. In this, you have 2 alcohols tied together in a chain, and so if you protonate one end in that first step, it's exactly the same as the last experiment. You now have the leaving group at the other end of a chain, and so you can go ahead and do an intramolecular SN2. Same idea, lose a molecule of water as the leaving group. There's a cycle now. All you did was tie the 2 things together, and if you deprotonate, you get this. Nothing much to that, but it's easy to get wrong. So make sure you're on top of stuff. Is anybody out there? Michael. Oh yeah, you can probably precipitate it. Yeah, maybe you change the solvent and precipitate it out. That's a guess, but maybe that would be something to try. Examples. You need to practice examples. You can see here at the top you're starting out with ethanol. It's a very simple way of making diethyl ether. Sulfuric acid heated up, intermolecular SN2, neutralize at the end, and you've got diethyl ether. Jessica. Yes, you can only get symmetrical ethers with the chemistry we've done so far. The next reaction which we'll do, you'll get the unsymmetrical. All right? Now, in this example, in this case, how do you know it's going to be intermolecular, not intramolecular? You only have 1 functional group. Yeah, the 1 functional group gives it away. At the bottom, you have 2 functional groups, therefore they can interact. So at the top, in the middle, you're looking at protonation. Now, will this thing break off on its own? Probably not, it's primary, right? So you'll get an SN2 slow, so you speed it up with heat, and you get that symmetrical ether. At the bottom, in this case, you protonate one end, and then you simply do this. It's kind of an intramolecular SN2, so it's not really an SN2 because it's not bimolecular, but it has the same characteristics. You're kicking out one leaving group at the end with the nucleophile at the other end. Brock. Fine question, young man. What's stopping it? I don't know. What's stopping it? Think about what's happening in this flash. The question he's asking is very good. It's this. What's stopping one molecule of this reacting with another molecule of that? And the answer is nothing. But they have to find each other in the solution. As opposed to the intramolecular version where they're already there. They're already together. You imagine, the time it takes for one molecule to find another and to line up properly. Whereas the one I'm showing at the bottom, it's already there. All it has to do is find the other end of the molecule and cyclize. So we'll say this in general. Intramolecular reactions will be faster than intermolecular reactions. We've seen that before. Pierce. That's unlikely if you have a small amount of acid, catalytic amount of acid. I mean, if you drowned it with acid, maybe that would be a problem. But you don't do that. I've forgotten your name after. Lauren, that's right, go on. No, we typically just go with that one. go with the intra? It's because you never say anything that I forgot your name, but now I know who you are. Tadler, that's right. Anybody else while we're at it? Any more for any more? Okay, so that's just SN chemistry. That's nothing tricky. This is much more useful and much more general because you can make unsymmetrical ethers by using this, what we call the Williamson ether synthesis. You've seen this before. We've alkylated alcohols in the past. You've seen this before. This, as Cole will tell you in SI, as I'll tell you in recitation, this kind of caps the alcohol. This is kind of a nice way of putting something on an alcohol that stops it being acidic, that maybe blocks it for maybe temporarily. But it certainly is a way of extending a synthesis. And as you saw just now, ethers are very important in medicine and pharmacy. So what we'll do is take an alcohol. And the nice thing about this is you can start with any type of alcohol, because as long as you can deprotonate it, you'll make it into a nucleophile. Now, what type of base am I using here? That's strong or weak? That is strong. If you had to give me an idea of what K was for that process, is it very large, 1, or small? It's very large, right? NaH is a super powerful base, and listen to the way I say this. Every molecule of the alcohol gets deprotonated. Okay, you get complete deprotonation with that base, and it does not come back. You get hydrogen gas, bubbles away, irreversible. So that thing is now over here. And this is an alkoxide species, like we saw in the previous chapter. That alkoxide species is basic itself, or in this case, if what you want to do is to put an electrophile in the way, and now you'll get alkylation. So what mechanism will this be in the second step? SN2. I'll start my arrow here because that's what's negative. I'll go here because that's delta positive. I'll kick out the bromine. And that gives me the ether. And because I've started with different pieces, I now can design a molecule that's more complex. It's not symmetrical. Now, what are some limitations here? If this becomes secondary or tertiary, what's the problem? Elimination. Somebody said it. Yes, you get E2 as well. Secondary, maybe not so much, but tertiary, it's all E2. So this is pretty much stuck with primary systems or methyl systems. Okay? If you did have a secondary system, and it was chiral, it was a chiral halide, what would happen? Inversion, right? It would be an inversion process because that's what the SN2 does. This is useful now. You can start adding things together which are much more complicated, and at the end of the day, what did we do this morning in office hours? About an hour? We did about 8 steps, Cole? 8 steps in one synthesis? That's where we should be by now. That's what we can do starting out with the simple stuff we did in 13 and adding this material. Make the molecule as complicated as you want. If you have an appreciably acidic proton, you'll go after it. You can take it off, and then you can alkylate it. So what's the pKa over here? 10, right? 10. So we'll use a powerful base just to make sure it does not come back, completely deprotonate. And then the example here is a simple primary alkyl iodide, and that will do an SN2. And this is an old pharmaceutical. It's not used much anymore, but it's an old analog of aspirin that was used as a pharmaceutical. So very useful. You can now alkylate oxygen very easily. And the motivation for this is a powerful nucleophile, wanting to attack that because you want to get the negative charge away from the O and onto the Br, because the Br is more stable as an anion. Simple SN2 ideas from last year. It's good, this stuff, because you can go back and review. You can look at some of the older stuff. Flying through this stuff now. There's another example. It's on the website. Listen to the little video. Listen to this later when it's on YouTube, whatever. Powerful base, any type of alcohol really. Take it off, take off the proton. H2 is lost irreversibly, form the alkoxide nucleophile. Make sure you understand that is now the nucleophile. If you put in some electrophile like this bromide, primary system, you'll kick out the bromide and you end up with a much more elaborate ether. Hello, Rihanna. Oh yes. I mean, that's just it, isn't it? I mean, you've done it by arrows. Mechanisms are all about arrows, and you've done it right there. As long as you've got those arrows in, you're fine. Lots of arrows. So very useful. There are some limitations again. This is just showing an example of methyl tert butyl ether, which I think they still use it in petroleum. I think it's still in gasoline as an additive. This is a non-symmetrical ether, but you have some limitations in terms of how you do this. If you had to design that molecule and come up with a synthesis, you can only do it one of those 2 ways. So in this case, we're doing the same thing, deprotonating from there, and then we're adding that. At the bottom, we can deprotonate, but what's the problem with this? Why doesn't this work? It's tertiary, and what's that mean? What's that about? It will give you elimination instead. It will not react through an SN2 because it's too crowded. It will not give you what you want. All right, so be careful. It's limited to sort of primary systems when you're attacking that electrophile. Going back, looking at other ways of doing this that you've already seen, maybe put it together now. Last year, we took alkenes and we treated them with mercuric acetate in water. We got that little three-membered ring, mercurinium ion, and then we opened it up and then we reduced off the mercury. And that gave us overall a hydration product in which a molecule of water seems to have added. And what was the point of this? Why was this useful? It prevented rearrangement of carbocations, right? You didn't get an open carbocation probably, so you don't get rearrangements. Well, all you have to do now to think about making an ether is swap that for something. What would you replace that with to make this useful for making an ether? An alcohol. You would need some kind of alcohol. So there you are. Very, very useful. Mechanistically the same. You're going to make the mercurinium ion, you're going to trap it with the ROH, you're going to get rid of the mercury in the second step, and you can pretty much choose what you want there. As long as your alkene works, you're fine. Go back and review. That's just adding a little bit of extra detail to last year. The toolkit is getting bigger and bigger. You won't be able to carry it soon, right? There's a lot of stuff in here now. Now, for you, this is a good chapter because there isn't that much here. But you can do a lot with it, right? There aren't only two reactions. There's SN1 and SN2 in this whole chapter. But you have to be able to be ready to when to do what. I've already said earlier that these types of compounds are very useful as solvents because they don't react with very much. But you can make them react if you treat them with a powerful acid such as HI or HBr, and then they do what we call cleavage chemistry. They break apart. And the mechanism of this is nothing more fancy than a bunch of protonations and a bunch of SN2s. What we need here is an excess of this. So if you see that written as such, that means there's more than one equivalent, more than one mole of that reagent. And you think about what we've done before in the past, this should follow on. This should be fairly straightforward. What would you do in this reaction first? You've got this pair of lone pairs here, and you have an acid. What should we do? Protonate. Pick up a proton. If you protonate, then you ought to then be able to think about the intermediate species. We should be here by now. And you have X minus floating around as the counter ion. How on earth do I get there? What type of chemistry will I need to do to get there? SN2. Nucleophile will have to come in, kick this out, and that symmetrically, it doesn't matter which end goes first. They're both the same. Kick that out, you'll make one equivalent of whatever this happens to be, and you'll make one equivalent of that. You have excess HI. So you protonate again and kick it out again. That was last semester. That was the SN2 that you did. If you had to think about down here, which end of the molecule do you think reacts first? Do you think you react on the right first or on the left first? On the right. Why? Less sterically crowded. Easier to get to, so it should give you a faster SN2 if indeed this is SN2 chemistry. So little details, nothing more complicated than we've seen before. Just bringing in some of last year's stuff and making it now applicable, making it useful. So the take home from this is that ethers don't do very much unless you cook them up with acid. So try not to do that, unless you're trying to do that. Okay, there's the mechanism. You can see a simple protonation in the first step. Formation of this, which is always a good leaving group. The argument then is which end do you attack first? Most likely the less crowded end, which is right there. That's an SN2 reaction, and away we go. We're left with one of the products right there, finished. I have a second alcohol. I have an excess of HBr. You already know that alcohols react with HBr, and you'll get this type of chemistry to give those two products. So go back and review the SN2. Useful chapters. Useful chapter just for consolidating. Okay, I'm going to mention these things. This is not desirable. Let's put it that way. You do not want this to happen. This is bad. Every now and again, we have a safety inspection in our department, and one of the things they are very keen on is checking your bottles of ether. Okay, because ethers have this very annoying propensity to react with oxygen. So how do you avoid that? I mean, you could think about deoxygenating your solvents and putting, trying to avoid any oxygen in there at all, but that's expensive and difficult to do. And what we tend to have to do is just cycle the ether, get rid of it. If it's been there for more than the prescribed amount of time, you get rid of it, you throw it away, or dispose of it carefully. And the reason behind this is that they will react with oxygen to form peroxides, and peroxides are explosive. And this can be a real issue, right? You can see when you get into the lab, I'm not sure what they do exactly now, but when I was in school, the ether came in a metal can with a metal screw cap. And if that thing rusted, okay, the metal screw cap rusted and you had to work to get it off, you're creating friction. And if this thing is old and you've got peroxides built up in there and you try and unscrew this thing, it'll blow up. The peroxide will detonate. So what we need to do is be careful. The chemistry behind this is quite straightforward, but it's detrimental. So anytime we deal with ethers, we've got to keep an eye on their, for lack of a better phrase, sell-by date, right? You've got to keep an idea when you bought it. And what you see is that oxygen behaves as a diradical. So you can imagine a mechanism here where oxygen reacts with hydrogen here, and you produce a radical that looks like that. And why would you put the radical there? Let's see if we remember this stuff. Why would you put the radical there on this carbon and not down here? What are radicals missing? It's more stable, Ms. Tadler. Why is it more stable? Resonance delocalization from the oxygen lone pairs. So this is actually regioselective. And you can imagine now a radical picking up the oxygen, going over here to give this species over there, and then that reacting with some starter material again to give this peroxide. And you can identify those steps as being initiation, propagation, termination, just like we did last year. But it gives you a peroxide, and those hydrogen peroxides you've got to be careful with. They're not to be messed with. All right, so there's an FYI. Be careful with the peroxides. And I think when you get to do the Grignard experiment, look at this again, and think about what we talked about today in terms of the properties of ethers. You've got to be very careful with them. Here's the actual mechanism from the textbook. In this case, the initiator probably is oxygen itself, rips off a hydrogen, form a radical next to the oxygen in the ether, couple with the O2, because this is a diradical, and then all this needs to do is get a hydrogen from another molecule and produce that. Whole bunch of initiation, propagation steps. And at the end of the day, what type is that? That's termination, right? How much of that do you think you'll get? Very little, because you don't have many radicals at one time. So this is key, right here, and there's your peroxide. Right, now, I'm going to start epoxides today. I think these are the most interesting compounds in this type of setup, because they are useful. They do react. So I've got different heterocycles here. Let me use that word again so that we're familiar with it as we move on. Hetero, different. Cycle. A heterocycle is any molecule that has a cycle and at least one atom isn't carbon. So we've seen this with pyridine. We've seen this with epoxides that we've already built. Now we'll find out that some of the nomenclature here is kind of old and kind of not that interesting. You don't need to worry about oxetane, oxalane, and oxane. We'll deal with those later when we talk about carbohydrates. But at the end of the scale here, that's very reactive. Why? Strained, less so, less reactive, less so, less reactive, right? Not so much strain. When you get to the six-membered rings, very little strain. So what we've got here is a little discussion of these epoxides. And you can see here, different names. Part of this is historical, part of it is useful, part of it is things like, in technology, you go to Home Depot or Lowe's or something, you can buy epoxy resins and glues and stuff like that. Very useful, and the nomenclature is stuck. Get it? Stuck, glue. We've got to know both of these so that you can handle the outcomes here. We'll find that epoxides do a lot of chemistry. That will be very useful for synthesis, and we'll be able to add on to things that we've already done. Now, this nomenclature stuff here, it doesn't matter which one you use. Okay, just be aware of each. This one is a bit of a giveaway. Epoxy, epoxide. And the epoxide is between carbon 2 and 3. So that's where that comes from. At the bottom, you're classifying it as an oxyrane, as an epoxide. So it's very similar to stuff we've already done. In this case, there's the oxyrane right here, and this is carbon 1, and this is carbon 2. I don't mind which one you look at. I don't discuss this an awful lot. It might show up in a question. there's a molecule with a name. Here's something that it needs to be done. Here's a mechanism you need to do. But it's a giveaway. It's either oxirane or epoxy, and that tells you it's an epoxide. These things are all over the place. These things are very important in cancer biology, if anybody's interested in that area. You can see here an epoxide inside this type of material, epothalones A and B, natural products that have been isolated and actually have some anti-cancer properties. That epoxide might well have something to do with the mechanism of this material. Okay, we'll talk a bit more about carcinogens later on, where epoxides are reactive. They do open up, and if they open up when they're being attacked by DNA, that can be a problem because then you get mutations. We'll deal with that a bit later. So epoxides are everywhere. There's another one. I have no idea how to say that, so I won't even try. But again, you can see the epoxide here, and these compounds have been isolated and tested and apparently have some use in the clinic. So they are important things. Now, how do you make them? How do you make epoxides? Again, this is a review. You can start out with an alkene. And alkenes were our simplest starter material from last term in terms of the breadth of chemistry that they did and the molecules that you could make. Why is that reactive? Why is that molecule reactive? Lone pairs next to each other, right? Oxygen-oxygen bonds are always weak because they repel and they want to break apart. So we can transfer one of those O's to an alkene and give us the epoxide. What type of addition was it? Look at this. Look at the product. Look at the wedges. There's a syn addition. And syn additions typically were concerted or stepwise. Concerted, right? And this thing was landing on top. I think I have a mechanism in a second. You can use various types of starter material here. We generically just wrote R last year. MCPBA down there. This has nothing to do with anything. This is just historical. It's actually, I believe, a byproduct from a drug synthesis, and they throw it away otherwise, and we turn it into MCPBA. So that chemistry, that part of the molecule does not do anything. But you have choice now. You have advantages now. Peroxyacetic acid is probably water soluble. If you want to deal with these things in water, you can use something like that. Do you think this is water soluble? Probably not. Right? So if you want to do a reaction in organic solvents, use MCPBA. But they both do the same chemistry. In terms of mechanism, go back and look at that. It's on my website so that we're okay with it. You get a syn addition, and if the starter material is chiral, maybe you put something over here to break up the symmetry. How many products will you get? 2, and they will be related as enantiomers. Okay? Enantiomers in that case. Another way of making epoxides is by doing this type of reaction. You can see here that the stereochemistry, let's just talk about this for a second. There's a word that describes this. The stereochemistry of the starter material dictates the stereochemistry of the product. Stereospecific. Stereospecific. So in this example, you've got the cis alkene, and you end up with the 2 R groups on the same side in the product. What does that tell you? What does it tell you about the mechanism? Stepwise or concerted? Concerted, right? Because if those 2 R groups are stuck like that, everything happened at once and you had no possible rotations. So this is a concerted process. And if you start out with the trans, where the R groups are on the opposite side, you end up with the trans product the same way. And those 2 are stereospecific. Well, then you can also think about doing this. We started out with alkenes and we also added bromine and water. We got a bromohydrin product. Again, if you're not sure about where that came from, go look at the book, go look at my website, and that's something that we have dealt with in the past. That wasn't concerted, was it? And why did it get a trans outcome? Stepwise, right? Bromonium. You went through one of these things. We spent a lot of time worried about what this thing was about. Br adding to either top or bottom to give you a modified carbocation. And in the second step, the water came in as a nucleophile, and you ended up with the anti-addition. So that was a way of getting functional groups onto the molecule to set up to make an epoxide. What do you think I need to do? If I want to turn this into an epoxide, I need to do that. How do we do this? Is that a strong nucleophile or a weak nucleophile? Weak. How do you make it a stronger nucleophile? Deprotonate it. So you take a base, deprotonate, make it O-, and then away we go. And here's from the book the mechanism. Hydroxide will work, hydride will work, NH2- will work. take off that proton, make a good nucleophile, and there we get the epoxide. Right, discussion here. You're making an epoxide. Is that strained or unstrained? Strained. So that's counterintuitive. You're going from something that lacks strain to something that has more strain. How is that possible? If you're thinking about mechanism and starting to get this stuff, if that's going to happen, then something else has to happen that is better to compensate. So in this case, we are thinking about where the charges are. The charge here is O minus. The charge here is Br minus. Is that good or bad? Very good. Getting that charge from the O minus to the Br minus is so good that you can make an epoxide at the same time. Okay, so you're making up for the fact that the epoxide is strained by the fact that you're swapping an O minus for a Br minus. So it does work. It's a very nice way of making epoxides. You have two ways: add an alkene, an MCPBA, or do the bromohydrin process. So we didn't do much today, but we did a lot. If that makes any sense? We're getting there. Here we go. In terms of ways to do these things, MCPBA, solvents for this. If you practice in problems, you'll probably see stuff like this. Dichloromethane is a non-participating solvent. It'll dissolve things up, and you'll be able to make epoxides quite quickly. If you want to do this in the second method, either way. Depends what you have, fine. Usually in the lab we would do this one. Maybe on bigger scale we might do this one. So in terms of stereochemical outcomes, we need to go back and think about RNS and think about diastereomers and all that sort of stuff. And we can see now that in both cases, the reaction seems to be stereospecific. And in this case, the methyl groups, keep an eye on them, are on opposite sides of the alkene. And on this one, they're also on opposite sides. So that tells you everything happened at once in terms of making that epoxide. Over here, this one is in front, this one is in back. So how do you get two products? How is it possible to get two products? It's planar. Go on. You can attack from the top or the bottom, or the front and the back. And you're going to get two outcomes because of that. Good stuff. Right. I'm not going to spend a lot of time on this. We'll do this later when we get to the biochem part at the end. But these types of epoxides are becoming more important, and we're starting to understand more about them in nature and in biochemistry, and they're typically problematic. Okay, you can see here, it's quite easy to be able to oxidize pharmaceuticals like this carbamazepine, and we can then think about how nature would use these materials to maybe expel. Okay, how does your liver get hold of an organic molecule and get rid of it? One way is to take the epoxide and to do exactly what we just did and think about opening it up. Why is the stereochemistry here trans? Okay, this has to come in from the back, and this has to open up like so, and you get a trans outcome. And then we're going to stick something on here. Later on, we'll see that's a carbohydrate, very water soluble, and so we'll link that to here, and that helps us get rid of these materials. Okay, so epoxides are associated with metabolism, and we'll have to deal with that in the near future. But at this point, we're really interested in the chemistry. Michael. That's actually a urea. We'll deal with that in the near future. Okay, I'm going to stop there. Recitation today, bring your questions. I need to be gone by 4, so get hold of me before then.